Imagine a spacecraft leaving Earth with the sun ahead of it, not as a symbol on the horizon, but as the destination. At first, nothing looks impossible. The sun still appears like the familiar bright disk that warms rooftops, glints on oceans, and marks the slow turning of ordinary days. Behind the spacecraft, Earth is still close enough to look blue, soft, and alive, wrapped in the atmosphere that has always stood between human skin and raw starlight. But that familiar sunlight is already an edited version of something much more severe. Earth makes the sun livable. Its atmosphere scatters and filters light. Its magnetic field helps redirect charged particles. Its clouds, oceans, winds, ice, and rotating days spread heat into weather, instead of letting one face of the planet simply bake without relief. From the ground, sunlight becomes morning warmth, season, and shadow. In space, without those protections, it becomes energy arriving directly across emptiness. So, what would actually happen if you began moving closer, not in a fantasy ship immune to physics, and not in a simple story where everything instantly bursts into flame? The real answer is slower and more interesting. First, Earth's invisible protection would fall behind. Then the sunlight would begin to multiply according to distance. The spacecraft would need to control what faces the sun, what hides from it, and where every bit of waste heat can go. Its shield would become a small, artificial night carried carefully through impossible brightness. Then the quiet failures would begin. A sensor warms beyond its ideal range. A radiator loses the clean angle it needs. A communication window closes behind solar glare. Radiation increases. The spacecraft enters the sun's outer atmosphere, where plasma magnetic fields and charged particles make ordinary ideas of heat and weather begin to fail. Closer still, the visible sun stops looking like a destination and becomes something stranger, a glowing layer of plasma with no ground beneath it. Tonight we follow that journey step by step, calmly and carefully. What would fail first? How close could any real system come? And at what point would the sun stop being a place ahead of you and become an environment no human technology could survive? On Earth, sunlight feels gentle because we almost never meet it alone. We meet it through air distance, clouds, haze, water, vapor, dust, and sky. It arrives softened by a planet. It falls across windows, trees, roads, grass, skin, and water, and most of the time, it becomes part of the background of life. We wake with it, work beneath it, grow food through it, and measure the passing of years by the way it changes, angle over fields and rooftops. That familiarity is powerful, and it is also misleading. Sunlight does not begin as something mild. It leaves the visible surface of a star and crosses space as electromagnetic radiation. It spreads outward in all directions, thinning with distance, but still carrying enough power by the time it reaches Earth to drive winds, evaporate oceans, move climate systems, feed plants, and warm the ground beneath every living landscape. Above Earth's atmosphere, facing the sun directly, each square meter receives roughly the power of a strong electric heater. On the ground, that number is softened by clouds, air angle reflection, and time of day. In space, the light is cleaner, sharper, and more direct. It does not come with a breeze. It does not come with shade that still sits inside warm air. It comes as energy crossing vacuum. The reason we can live beneath it is not that the sun is gentle. The reason is Earth. Earth does several things at once. The atmosphere absorbs some wavelengths and scatters others. The ozone layer reduces much of the ultraviolet radiation that would otherwise damage living tissue far more severely. Clouds reflect light back into space. Air carries heat from one place to another. Oceans store warmth and release it slowly. The rotation of the planet gives most regions a rhythm of day and night exposure and cooling sunlight and rest. Even the blue sky is a sign of protection. It tells us that sunlight is being scattered before it reaches our eyes. The daytime sky does not show us the sun as it appears in empty space. It shows us sunlight after air has taken hold of it, redirected it, colored it, and made it part of a planetary atmosphere. That atmosphere is thin when seen from orbit, but for life it is enormous. It gives pressure to the body. It gives oxygen to the blood. It lets heat move by contact and wind. It turns light into weather. It softens the difference between sunlit ground and shaded ground. It allows clouds to pass between the surface and the star, changing the brightness from minute to minute. It makes sunlight something that can be lived inside. If that atmosphere vanished, the sun would not need to move any closer to become dangerous. The shadows would become darker and sharper. Ultraviolet radiation would reach the surface with far less filtering. Heat would no longer spread through air in familiar ways. There would be no breeze to cool skin, no pressure to hold water in the ordinary state the body depends on, no blue sky to diffuse the light. The sun would be the same distance away, but the relationship would be completely changed. This is the first step in understanding the journey. The sun is not safe at Earth because it is harmless. It is safe because Earth has made a narrow arrangement with it. At this distance, with this atmosphere, this magnetic field, these oceans, this rotation, and this chemical balance, solar energy becomes livable. Change the distance, remove the filters, or lose the regulating systems, and the same star begins to show another nature. On a warm afternoon, it is easy to forget this. A person can step into the shade of a tree and feel relief. A cloud can pass over the sun and cool a field. A lake can hold warmth after sunset. The body can sweat, air can move, and the skin can interpret sunlight as weather rather than radiation. Everything about the experience suggests that the sun belongs naturally to the world, but the world is doing much of the work. A person standing in a field is not exposed to raw solar energy in the way a spacecraft is. They are standing beneath a moving atmosphere inside a magnetic environment on a rotating planet with water and weather. They are protected by things too large and constant to notice. The comfort of sunlight is not only a property of the sun, it is a property of the whole Earth-Sun relationship. From orbit, that relationship becomes visible. The atmosphere thins into a faint blue line. The sun shines against black space rather than within a glowing sky. The boundary between day and night on Earth becomes sharp, a curved line moving across oceans and continents. On the planet below, evening may feel gradual and soft. From above, it is clear that the world is turning through a stream of light. A spacecraft near Earth already has to respect that stream. One side may face direct sunlight, while another side faces deep space. The difference can be severe because there is no surrounding air to even things out. A surface in sunlight absorbs radiation. A surface in shadow radiates heat away. Heat has to move through structures, fluids, pipes, insulation, and radiators. The spacecraft must remain internally stable, while the outside offers extremes rather than comfort. This is why thermal control is basic to spaceflight even near Earth. Every spacecraft is designed around heat. It must keep electronics from overheating. It must keep batteries within safe limits. It must keep fuel lines, instruments, and structural parts from drifting outside their working ranges. A spacecraft can be too hot on one side and too cold on another. It is not floating in a single temperature, It is balancing between sunlight and darkness. For humans, the dependence is even deeper. A human being cannot simply be placed in sunlight and space. The body needs air pressure, oxygen, temperature, regulation, water balance, and protection from radiation. A spacesuit or spacecraft is therefore not just equipment. It is a small, artificial world, a temporary replacement for the services Earth normally provides without asking for attention. This is still before the journey has moved inward. The sun has not grown larger in any dramatic way. Its light has not yet multiplied. The spacecraft is still near the same solar distance where Earth orbits, and already sunlight has stopped being ordinary. It has become a thing that must be managed by surfaces, coatings, orientation, insulation, and machinery. The deeper cause is distance. Sunlight spreads outward from the sun across larger and larger spheres. At Earth's orbit, the energy has been diluted by 93 million miles of expansion through space. If you move farther away, the same total light is spread over even more area, and each square meter receives less. If you move closer, the reverse happens. The same solar output is spread over less area, and every exposed surface receives more. This rule is called the inverse square law. It is simple enough to feel without equations. Move twice as far from a light, and the brightness falls to about 1/4. Move half as far, and it becomes about 4 times stronger. Distance does not soften light gently. Distance changes the whole energy balance. The sun at Earth is already powerful. The sun closer in becomes something else. That is the quiet engine of the whole journey. At Earth, the sun's energy can become climate photosynthesis, rivers, winds, and seasons. At the wrong distance, that same energy overwhelms the systems that try to live with it. A planet needs the right orbit and the right atmosphere to make starlight useful. A spacecraft must create its own protection, and the closer it goes, the more difficult that creation becomes. So, before the spacecraft fires a major engine or begins falling inward, the first transformation is mental. We have to stop imagining sunlight as a warm presence in the sky. We have to see it as a continuous flow of energy from a star made livable only by a planetary arrangement so constant that we almost never recognize it. The warmth on a wall, the softness of a cloud shadow, the blue of the sky, the cooling of evening, all of these are evidence of protection. Without that protection, the sun is more direct, not evil, not angry, not attacking, simply direct. A star radiates. Space carries that radiation. Matter absorbs, reflects, or transmits it. Living bodies survive only when the surrounding environment keeps those interactions within narrow limits. Earth has done this for us so completely that the protection has become invisible. A journey toward the sun begins by making it visible again. The spacecraft has not yet reached Venus-like distance. It has not crossed Mercury's orbit. It has not entered the corona or approached the visible solar layer. But the central truth has already been established. The sunlight we know is not raw sunlight. It is Earth's version of sunlight filtered and negotiated by a planet. Ahead, that negotiation will weaken step by step. The spacecraft will carry its own air, its own pressure, its own cooling, its own shielding, and its own thin boundary between life and space. Earth will fall behind as a bright blue shelter. The sun ahead will look familiar for a little while longer, but the familiar feeling will no longer be trustworthy. The light has always been energy. The journey only makes that impossible to forget. The spacecraft does not enter the sun's danger all at once. At first, Earth is still near. The planet may remain large behind the spacecraft, a blue-white curve in the darkness with clouds curling over oceans and continents. The sun ahead may not seem much larger than before. The light has not yet multiplied into the extreme intensities, waiting farther inward. If you judged only by the view, the journey might still seem calm. But a boundary has already been crossed. The spacecraft has left the world where survival was provided by the planet. On Earth, the body lives inside a deep support system. Air presses from every direction. Oxygen arrives without machinery. Carbon dioxide leaves the lungs and disappears into a global atmosphere. Heat moves through air and water. Moisture does not boil away from exposed tissue. Radiation from space is partly filtered. Charged particles from the sun are shaped and deflected by Earth's magnetic field. Gravity gives the body orientation and pulls fluids downward in a familiar way. Most of this is unnoticed because it never stops. A person does not usually feel atmospheric pressure as protection. They do not see the magnetosphere. They do not hear ozone absorbing ultraviolet radiation. They do not sense the atmosphere redistributing warmth across landscapes. These things are too constant to become dramatic. They are the background of being alive. A spacecraft cannot treat them as background. When it carries people away from Earth, every invisible service must be replaced by systems that can fail. The cabin must hold pressure. The air must be circulated, filtered, and chemically balanced. Oxygen must be supplied. Carbon dioxide must be removed. Water must be stored and recycled. Temperature must be controlled. Waste heat must be moved. Radiation exposure must be watched. Every layer of ordinary life becomes a task. Leaving Earth is therefore not only travel, it is a transfer of responsibility from planet to machine. Inside the spacecraft, this transfer may feel peaceful. The cabin lights are steady. Fans move air. Displays show pressure, oxygen, humidity, temperature, and power. The crew, if there is one, may float through the interior with practiced calm. A cup, a tool, a strap, a sleeping bag, a tablet screen. Each object belongs to a quiet human routine. Outside the hull, there is no routine at all. There is vacuum, unfiltered sunlight, darkness, particles, and radiation. There is no air to breathe, no pressure to stabilize the body, no wind to carry heat away, no weather to soften the division between sunlight and shadow. The spacecraft is a small artificial environment, surrounded by conditions that would make human life impossible almost immediately. This is the first physical correction to the common question. If you were simply outside, near Earth's orbit, you would already be in lethal trouble. You would not need to be close to the sun. The body cannot survive vacuum without protection. It needs pressure, oxygen, and thermal regulation. It needs the fluids inside it to remain in a stable range of temperature and pressure. It needs delicate tissue in the lungs and eyes to be protected from exposure. Direct sunlight in space would add more danger, but the first failure would be more basic. The body is a planetary organism. A spacesuit can briefly solve some of these problems, but a spacesuit is not clothing. It is a miniature spacecraft shaped around a human body. It holds pressure, provides oxygen, removes carbon dioxide, cools. The astronaut protects against micrometeoroids, filters sunlight through a visor, and gives the body a private artificial atmosphere. Even then, it has limits in duration, radiation protection, thermal range, mobility, and reliability. A crude solar approach would need something far larger than a suit. It would need a spacecraft that functions as an artificial Earth. Not a complete Earth, of course, but a small controlled interior where the essentials of Earth are imitated. The closer the spacecraft moves toward the sun, the more this artificial Earth must defend itself from an environment that becomes less and less forgiving. Thermal control is one of the first tests. In popular imagination, space is cold. That is partly true, but incomplete. Space is not cold in the same way air is cold. There is no surrounding atmosphere to touch the spacecraft and carry heat away. Objects lose heat mostly by radiation, sending infrared energy into space. They gain heat by absorbing sunlight, by internal machinery, by electronics, and by the warmth of crew and life support systems. This creates a strange condition. A spacecraft can overheat in sunlight and also freeze in shadow. One component can be warmed dangerously, while another must be kept from becoming too cold. A radiator needs a clear view of dark space to dump heat, while a solar array needs sunlight for power. Insulation must slow unwanted heat flow, but some heat must be moved efficiently to the right places. Every surface participates in the balance. Near-Earth engineers know how to manage this, but it remains a constant task. The spacecraft must turn carefully. It must use coatings, blankets, heaters, radiators, pumps, and sensors. It must monitor temperatures and batteries, computers, tanks, cameras, and structural parts. If a system becomes too hot, it can fail. If it becomes too cold, it can also fail. Thermal survival is not a single number. It is a choreography. Radiation adds another layer. Earth's magnetic field does not make space safe, but it helps create a protected region around the planet. Beyond that protection, a spacecraft is more exposed to energetic particles from the sun and from deep space. Solar particle events can send high-energy protons outward after flares or eruptions. These particles are not visible like sunlight. They do not appear as a bright wave through a window. They arrive as radiation-dose electronic disturbance and risk to tissue. For a crew, this matters deeply. Radiation damage is not always immediate. Some doses can cause acute illness. Lower or accumulated doses can increase long-term health risks. Energetic particles can also affect electronics flipping bits in memory or damaging components over time. A spacecraft moving inward would need a protected storm shelter, probably using dense supplies water or dedicated shielding to reduce exposure during dangerous solar events. But protection has mass. Mass is expensive in space. Every extra kilogram must be launched from Earth, accelerated, guided, cooled, protected, and eventually slowed or redirected. Add more shielding, and the spacecraft becomes heavier. Add more cooling, and it needs more power and more radiators. Add more redundancy, and it has more components that must be protected. Survival systems solve problems by creating new burdens. This is one of the quiet laws of the journey. Protection is never free. Even communication begins to depend on the environment. Near-Earth communication feels almost immediate compared with deep space. A spacecraft can send telemetry and receive commands with manageable delays. Mission control can watch systems interpret data and help respond. But as the vehicle moves inward, geometry begins to matter. The sun can interfere with radio signals when it lies close to the line of communication. Antennas may need to point in directions that conflict with thermal safety. The spacecraft must be able to act without constant help. Autonomy becomes part of survival. If a system overheats, if a solar particle event begins, if attitude control drifts, if the shield must be kept aligned, the spacecraft cannot wait for a long conversation with Earth. It needs sensors, software, and fault protection routines that can respond quickly. It must know when to shut down an instrument, enter a safe mode, reorient conserve power, or prioritize crew safety. The machine has to carry its own caution. It does not feel caution, but it must perform it. It must behave as if it knows the difference between a harmless drift and a dangerous one. It must keep track of orientation, thermal load, radiation power pressure, and communication. It must maintain a livable interior while the outside offers no forgiveness. This is still not close to the sun. That fact is important. The spacecraft has not yet reached the region where sunlight is several times stronger than at Earth. It has not entered the corona. It has not come near the photosphere. The sun still looks like a distant disk. yet survival has already become fully artificial. The traveler now lives inside a machine that must replace a planet. That machine is a bubble of pressure in vacuum. It is a pocket of breathable air in a place without air. It is a cooling system in a realm without wind. It is a radiation shelter beyond the ordinary protection of Earth's field. It is a small, organized interior moving through conditions that would instantly overwhelm the unprotected body. This changes the emotional meaning of the trip. A journey on Earth usually moves across a world that remains basically supportive. A desert may be harsh, but there is still gravity, air pressure, a horizon, and ground. A mountain may be cold, but the atmosphere is still there. A storm at sea may be dangerous, but the ocean still behaves as a surface, and the sky still contains air. In space, the traveler carries the support system. The spacecraft is not simply transportation. It is the environment itself. If that environment remains stable, the crew lives. If it fails, the surrounding universe does not provide a second layer of help. The boundary between survival and death is the hull, the seals, the pumps, the electronics, the shield, and the software, keeping them coordinated. Earth behind the spacecraft becomes more than a home planet. It becomes the image of everything the machine is trying to imitate. The blue atmosphere below is pressure, radiation, protection, thermal balance, chemistry, water, and weather. The spacecraft contains only a tiny engineered echo of those things. It can function for a time, perhaps a long time, but it must never forget that it is an imitation. A planet can absorb mistakes. A spacecraft has to manage them. As the journey begins to move inward, the first changes may be subtle. The sun grows slightly brighter. The thermal system adjusts. The spacecraft's control software calculates new attitudes. Solar arrays may be angled differently. Radiators may need more careful exposure to deep space. Radiation monitors remain watchful. The crew may not feel the change, but the vehicle does. The instruments notice before the body does. This is how the sun will first begin to assert itself. Not through a fire outside the window, but through numbers drifting upward. More power on sun-facing surfaces. More heat load. More glare for optics. More concern about orientation. The same sunlight that Earth turned into afternoon is becoming an increasingly direct engineering demand. The journey is leaving the zone where the sun can be treated as familiar. Ahead lies the first multiplication of light. Venus-like distances will make the change noticeable. Mercury-like distances will make it impossible to ignore. Beyond that, the spacecraft will need to become more specialized, more disciplined, and more dependent on keeping the right parts exposed and the wrong parts hidden. For now, the most important event has already happened. Earth's protection has fallen behind. The planet no longer filters the light, no longer provides pressure, no longer shares the work of heat, and no longer surrounds the body with the invisible assumptions of life. The spacecraft is alone with its systems, and the sun, still distant but no longer softened by Earth, waits ahead as a growing physical load. Moving inward at first feels almost too gradual to trust. There is no visible gate between Earth's orbit and the deeper inner solar system. There is no band of color in space, no warning line, no sudden change in the darkness. The sun grows larger slowly. Earth shrinks behind the spacecraft. The view remains silent and clean, and the mind may struggle to believe that the environment is changing in a meaningful way. The instruments do not struggle. They register more energy on every surface facing the sun. The change is not dramatic in appearance, but it is exact. The spacecraft is entering a region where sunlight is no longer the familiar intensity that Earth receives. It is becoming stronger by geometry, and geometry does not need to look threatening in order to be dangerous. This is the inverse square law beginning to matter in practice. At Earth's orbit, sunlight has spread across a sphere with a radius of about 93 million miles. Move inward, and the sphere becomes smaller. The same solar power is now distributed over less area. Each square meter receives more. The closer the spacecraft travels, the more energy arrives at its surfaces every second. The rule sounds gentle when spoken slowly. Half the distance means 4 times the sunlight. 1/3 the distance means 9 times the sunlight. But inside a spacecraft design, those numbers are not gentle. They mean more heating, more glare, more stress on coatings, more demand on cooling systems, more pressure on every choice of angle and exposure. The sun has not changed. The spacecraft has changed its place inside the sun's radiation. The first major threshold is Venus-like distance. Venus orbits closer to the sun than Earth, not close enough to feel like the edge of the star, but close enough for the difference to matter. At that distance, sunlight is roughly almost twice what Earth receives. This may not sound impossible. Twice the sun might suggest a harsh summer day, a desert noon, a bright glare off pale stone. That image is wrong because it belongs to Earth. On Earth, a bright day still comes with air pressure weather and heat exchange. The ground warms the air. Air moves across skin. Clouds may interrupt the light. A shadow remains inside an atmosphere that has temperature. In space, at Venus-like distance, the spacecraft faces radiation directly. There is no surrounding air to carry away heat, no cloud bank to soften the exposure, no wind to help a surface cool. The ship must manage every watt by design. At this point, the spacecraft's design begins to reveal a truth that is easy to miss from the outside. Nothing on the vehicle is merely decorative. A surface is not just a surface. Its color coding, texture, angle, and thickness all decide how it behaves under sunlight. A dark panel absorbs more energy. A reflective layer sends more away. A blanket of insulation slows heat from moving inward. A radiator is not simply a metal plate, but a carefully placed exit for heat that the spacecraft cannot keep. Near Earth, these choices matter. Near the sun, they become destiny. Imagine the spacecraft slowly adjusting its solar arrays as it moves inward. At first, the panels face the sun more openly, gathering power the way a leaf gathers light. But as the journey continues, that same exposure becomes dangerous. The panels may need to tilt, presenting only a narrow edge to the sun, collecting enough energy without absorbing too much heat. Power is abundant now, but usable power still depends on keeping the collectors alive. This is one of the first moments when the journey stops feeling intuitive. More sunlight does not automatically mean more freedom. It can mean more caution. A system that once pointed proudly toward the sun now turns away from it, not because the mission has failed, but because survival requires restraint. The spacecraft is learning to accept only as much of the sun as it can afford. Inside the cabin, the change might appear as a quiet update on a display. Solar array angle adjusted, thermal margin reduced, radiator load increased. No alarm sounds, no one floats in panic. But the spacecraft has entered a new relationship with the star. It is no longer simply collecting light. It is negotiating with it. And the negotiation will only become stricter. A sun-facing surface reflects some incoming light and absorbs the rest. The absorbed part becomes heat. That heat may conduct inward, spread through structural layers, move through fluid loops, or be radiated away. If the material is dark, it may absorb more. If it is bright or specially coated, it may reflect more. If it is angled carefully, it may reduce direct exposure. If it is exposed carelessly, it becomes a problem. At Venus-like distance, a well-designed spacecraft can survive. Many robotic missions have traveled inward and operated in this part of the solar system. But for our imagined crewed descent, this is where the first practical restrictions begin to feel permanent. The sun is no longer simply a direction for power generation. It is a load that must be controlled. The solar arrays reveal the paradox. Far from the sun, spacecraft often struggle to collect enough energy. Nearer the sun, there is abundant light, but the light brings heat. A solar panel may produce more electrical power, but it also warms. Its efficiency can fall as temperature rises. Its materials can degrade. Its orientation must be chosen not only to collect energy, but to avoid damage. More sunlight is not simply more usefulness, it is more responsibility. This is one of the first reversals of the journey. The thing that powers the spacecraft also threatens it. Past Venus-like distance, the spacecraft moves toward Mercury-like conditions. Mercury receives sunlight several times stronger than Earth does, often around 6 to 7 times at its average distance. From that region, the sun would appear larger and more commanding. Its disk would occupy more of the sky. Its light would no longer feel like a bright version of Earth's sunlight. It would feel like a different environment. Mercury itself teaches a useful lesson. The planet has almost no atmosphere to spread heat around. Its sunlit surface can become extremely hot, while regions in darkness can become bitterly cold. It is not simply a hot world. It is an exposed world. Sunlight and shadow are allowed to separate sharply because there is no thick atmosphere to moderate them. A spacecraft near Mercury faces a similar principle, but with greater complexity. One side may be flooded with intense solar radiation. Another side may be pointed toward cold space. Inside, electronics tanks, batteries, and crew systems must remain stable. The spacecraft must prevent the sunlit side from overheating, while also preventing shadowed systems from falling below acceptable temperatures. It is not only fighting heat, it is maintaining order between extremes. At this stage, ordinary spacecraft assumptions begin to narrow. Materials comfortable near Earth may be strained. Adhesives can weaken. Coatings can darken. Insulation can change performance. Seals, lubricants, optical surfaces, cables, and connectors can become points of concern. Electronics may still operate, but with reduced margin. Cameras and star trackers must avoid glare. Windows, if they exist, become carefully controlled hazards rather than simple views. Human passengers might still feel calm inside the cabin. That calm would be deceptive in an important way. The air could remain cool. The pressure could be normal. The lights could glow softly. The crew might eat sleep exercise, check instruments, and hear the familiar hum of fans. The danger would not necessarily enter the cabin as heat on the skin. It would first appear as shrinking margins in the systems that preserve the cabin. A coolant loop works harder. A radiator approaches its limit. A solar array rotates to reduce exposure. An optical sensor is powered down because glare is too strong. A battery management system keeps a closer watch. A thermal warning appears, disappears, and appears again. Nothing has failed. Not yet. But the spacecraft is using more of its ability simply to remain ordinary inside. The farther inward it moves, the more ordinary cabin life depends on extraordinary protection. This is the step-by-step reality of approaching the sun. It is not a sudden wall of death. It is the slow conversion of distance into engineering difficulty. Each inward move asks more of the spacecraft. Each system that worked easily near Earth now needs stricter control. each exposed surface becomes more important. The vehicle must know not only where it is going, but how every square meter is facing the light. The sun also begins to affect observation. A camera cannot simply look where it likes. Sensitive optics can be flooded, heated, or damaged. A star tracker used for navigation may have to avoid the sun and bright glare. Sensors need baffles, filters, shutters, and protective modes. Human eyes are even more vulnerable. Looking toward the sun through inadequate filtering would be disastrous. The closer the spacecraft goes, the less direct seeing is allowed. The journey becomes increasingly mediated. The crew does not meet the sun with naked vision. They meet it through filtered images, readings, instruments, alarms, and models. The more powerful the light becomes, the more carefully it must be reduced before it can enter human understanding. This is an odd truth. To know the sun closely, one must allow less of it in. By Mercury-like distance, orientation becomes more than a convenience. The spacecraft begins to develop a preferred posture. Surfaces designed to face the sun must face it. Radiators must avoid it. Solar arrays may need to tilt. Instruments may need windows of exposure. Communication antennas may have to work within thermal constraints. The vehicle is becoming less free to rotate because every rotation changes its heat balance. Distance has become discipline. There is still deep space in most directions. There is still blackness. There are still stars. But one direction now dominates the spacecraft's life. Toward the sun, energy arrives with increasing force. Away from the sun, heat can be radiated into darkness. The spacecraft survives by respecting this asymmetry. It must decide which parts belong to day and which parts belong to night. That decision will become the basis of the next stage. At first, reflective coatings and general thermal design may be enough. Then specialized surfaces become necessary. Then protected instruments. Then stricter pointing. Eventually, a dedicated heat shield must take over as the main survival boundary. The spacecraft will stop being a vehicle that happens to have a hot side. It will become a machine built around one protected direction. This is where the phrase "closer to the sun" begins to feel less casual. Closer means more than a shorter distance. It means more energy per square meter. It means less tolerance for poor geometry. It means stronger glare, tighter cooling, greater radiation concern, and more dependence on systems that have to work continuously. Closeness is not only a position, it is a rising demand. The spacecraft is now leaving behind the idea that sunlight can be managed as background. Sunlight is becoming the main environment. A mission designed only for Earth orbit would not be enough here. A mission designed for the inner solar system must be built with the sun as a central constraint. Its materials, surfaces, electronics, power systems, instruments, and software all have to assume that light is not merely illumination. It is an incoming physical load that must be reflected, absorbed, redirected, or rejected. Or, the crew if present would know this mostly through procedure. They would not casually open an unfiltered shade. They would not point a camera directly without protection. They would not treat a thermal alarm as a minor inconvenience. They would understand that behind the cabin's calm, the spacecraft is spending more of its design margin with each inward step. A quiet number on a display could matter more than any dramatic view. This is how the sun begins to take control without appearing to move. It does not reach out. It does not change expression. It simply shines. The spacecraft enters regions where that shining is stronger. Every component, every coating, every sensor, every surface has to answer a question. The sun asks continuously, How much of this energy can you survive? At Mercury-like distances, the answer may still be enough if designed well. Beyond that, the answer becomes more fragile. The sunlight will grow from several times Earth's level to dozens, then hundreds of times in the realm of our most daring solar probes. The spacecraft will need a shield that is no longer a helpful layer, but the center of survival. It will need to hide most of itself behind a small, carefully maintained night. The first multiplication of light has changed the journey. The spacecraft has learned that moving closer does not simply make the sun larger. It makes every surface accountable. It makes every angle meaningful. It turns brightness into heat load power, into risk, and distance into a calculation that cannot be ignored. Ahead, the spacecraft must stop facing the sun as a whole machine. Only the shield can face it now. Beyond Mercury-like distances, the spacecraft's freedom begins to disappear. It can no longer behave like a vehicle that turns easily from one task to another. It cannot casually expose a new side for communication observation or maneuvering and then correct the problem later. The environment is too bright, too asymmetric, too strict. One direction has become dominant, and the whole machine must organize itself around that direction. At this stage, survival becomes a matter of facing. The heat shield must face the sun. That sentence sounds simple, but near the sun, it becomes the central law of the spacecraft. The shield is not only a strong plate at the front of the vehicle, it is the boundary between the part of the spacecraft allowed to meet the star and the part that must remain hidden. On one side, solar radiation strikes with overwhelming intensity. On the other side, instruments, computers, power systems, propellant lines, and perhaps a crew habitat must remain in shadow. The shield makes a small artificial night. That night is not wide. It is not natural. It is not forgiving. It is a geometric region created by the shield's shape, the spacecraft's orientation, and the exact direction of sunlight. If the spacecraft turns too far, the night shifts. If an instrument extends beyond the protected zone, it becomes exposed. If an antenna or radiator cannot operate from within the shadow, it becomes a thermal risk. The sun does not need to strike everything. It only needs to reach what cannot endure it. This is the principle behind real close solar missions. Parker Solar Probe. The most important reference point for this kind of journey survives not because every part of the spacecraft can tolerate the same extreme environment. It survives because its thermal protection system takes the direct sunlight while the sensitive spacecraft body remains behind it. The probe is compact, disciplined, and built around hiding. The shield itself is an elegant kind of engineering. It is not a massive wall in the ordinary fortress sense. Its power comes from a balance of materials and design. Carbon-based layers, lightweight insulating structure, and a bright reflective surface work together to keep the front hot and the back far cooler. The exposed face can endure severe solar heating while the systems behind it continue to operate. The shield does not make the sun safe. It makes a limited path through danger possible. That distinction is important. A shield is not victory over the sun. It is controlled exposure. The spacecraft survives by allowing one designed surface to take the punishment while the rest of the vehicle avoids direct contact. It refuses most of the light. It reflects what it can, slows what it cannot reflect, and gives the protected systems time to function. The achievement is extraordinary, but it is also humble. The spacecraft is not stronger than the star. It is carefully hidden from it. This is why orientation matters as much as material. A perfect shield pointed the wrong way cannot protect the spacecraft. A slight drift may expose a component that was never meant to receive direct sunlight. A solar array edge, a sensor housing a cable, an antenna joint, a radiator line, Any of these could become the first weak point. Near Earth, a small attitude error may be recoverable. Near the sun, recovery time is part of the danger. Imagine a tiny drift. The spacecraft's sensors detect that the sun is no longer perfectly centered on the shield. The difference may be small, perhaps too small for a human observer to feel dramatically. But a protected instrument near the edge of the shadow begins to warm. The attitude control system responds. Reaction wheels or thrusters adjust the spacecraft's body. Software checks whether the alignment is restored. A message is stored for later transmission to Earth. In a calm cabin, nothing may seem to happen, but the spacecraft has just defended its life. This is the kind of drama close to the sun creates. It does not need noise. It does not need fire. It happens in pointing angles, sensor readings, and thermal margins. A fraction of a degree can matter because the shield's shadow is the spacecraft's shelter. The closer the mission moves toward the sun, the more survival depends on keeping that shelter intact. Real solar missions need autonomy for this reason. Earth cannot be the immediate rescuer. Signals take time. Communication geometry can be difficult. The sun itself may interfere with radio paths. During critical close approaches, a spacecraft may operate largely on stored commands and onboard intelligence. It has to monitor itself, correct itself, and protect itself before humans can respond. The machine carries its own caution. It knows the sun through sensors. It knows its own position through attitude systems. It knows which temperatures are safe, which components are warming, which instruments can remain powered, and which must be shut down. It can enter protective modes. It can choose survival over observation. It can preserve the shield alignment even if other tasks must wait. This is where curiosity becomes secondary to posture. A spacecraft may have traveled inward to study the sun, but it cannot study recklessly. Instruments can only look through carefully controlled paths. Cameras need filters and protective doors. Particle detectors may sample the environment, but their exposure has to be considered. Some instruments hide until the correct moment open, briefly gather data, and return to safety. Even looking becomes a thermal decision. Solar Orbiter offers a useful image of this. Its heat shield protects the spacecraft, while instruments observe through selected openings. The vehicle does not simply face the sun with all its parts exposed. It peers from behind protection. This is close solar science, as a careful glance, not an open stare. For a crewed spacecraft, the same principle would become even more severe. The habitat would have to sit behind a forward shield, perhaps deeply nested inside layers of insulation, radiation, protection, and thermal control. The crew would live inside the shadow, not beside it. Their windows, if any existed, would be heavily protected or rarely usable. Most of what they knew about the sun would come through instruments, screens, filtered sensors, and delayed images. The sun would be nearer than ever, yet less directly visible. A human cabin would also make the problem harder. Robotic probes can be small, tightly arranged, and designed around a narrow set of needs. Humans require space, air, water, food, waste systems, exercise equipment, medical support, psychological stability, and redundancy. Every addition creates more mass, more heat, more surfaces, more possible failure points. The spacecraft becomes not only a probe, but a miniature world. The sun is hardest on miniature worlds. A probe can hide like a seed behind a shield. A crewed ship is larger, warmer, and more complex. It produces internal heat that must be rejected. It must maintain pressure and temperature across a living volume. It must keep people safe during solar particle events. It must provide emergency options. All of this must happen while the vehicle keeps its shield facing the star with relentless precision. The shield becomes the front wall of life. Behind it, everything depends on the artificial night. The crew sleeps in it, computers operate in it, water circulates in it, air moves in it, instruments wait in it. The spacecraft's interior is not simply protected by technology. It is protected by a geometry that must be maintained without pause. This changes how communication works. An antenna may want to point toward Earth, but the spacecraft cannot simply turn the whole vehicle if that exposes vulnerable surfaces. The communication system must be designed around the thermal posture. Sometimes data may be stored until the spacecraft is in a safer orientation or a better position. The most valuable measurements may be gathered during the closest approach and sent home later after the vehicle has survived the passage. Science waits behind survival. Power systems face similar constraints. Solar arrays closer to the sun receive far more energy, but too much light can overheat them. They may need to be angled steeply, exposing only part of their surface. Some designs allow arrays to retract tilt or present less area. The spacecraft may have more sunlight than it can safely use. Energy abundance becomes a management problem rather than a simple advantage. Cooling also bends around the shield. Radiators must reject internal heat into cold space, but they cannot be allowed to stare into the sun. They need shadow angle and view. A radiator that absorbs too much solar energy stops being a radiator in the useful sense. It becomes another heated surface. The spacecraft must therefore arrange its thermal exits as carefully as its protective front. Everything becomes architectural. The spacecraft is like a building with only one acceptable direction for its outer wall, one forbidden sky, and a narrow set of safe openings. Heat must travel through planned corridors. Data must leave through protected pathways. Instruments must look through selected windows. Power must be collected without inviting too much exposure. The whole machine is shaped by the need to keep the sun on one side of a boundary. There is a quiet beauty in this discipline. A spacecraft moving near the sun is not heroic because it charges forward without fear. It is heroic because it is careful. It survives by not wasting exposure, not turning unnecessarily, not forgetting where the danger is. Its courage, if we can use that word for a machine, is not boldness. It is alignment. The shield must face the sun. That repeated command is not poetic. It is practical. If the attitude system fails, the shield cannot protect the spacecraft body. If the spacecraft tumbles, the mission may be lost quickly. If the protected shadow shifts too far, the systems behind the shield may heat beyond their limits. The sun does not need to break through. The spacecraft can defeat itself by losing orientation. This gives close solar flight its tense stillness. From outside, the probe may look like a small object passing through emptiness. It may not appear to struggle, but internally it is constantly adjusting, sensing, correcting, and preserving its posture. Behind every stable image is a control system working to keep the star where it belongs on the shield, not on the spacecraft. A crew inside would experience this through rules. Do not command unnecessary rotations. Do not expose unprotected optics. Do not assume a window can be opened to light. Do not treat a pointing alert as routine. Do not ignore thermal margins. The sun would be the unseen authority behind every procedure, shaping the schedule, the communication, the observations, even the emotional experience of the journey. The closer the spacecraft travels, the more it must behave like a shadow moving toward fire. But again, fire is the wrong word if taken literally. The sun is not a flame in air. It is a star, and the spacecraft is moving through radiation and plasma. Still, the old image helps one thing become clear. The spacecraft's safety is not in facing the brightness openly. Its safety is in maintaining separation between what can endure the sun and what cannot. The next question follows naturally. What about the systems that cannot remain perfectly hidden? What about sensors that must see antennas, that must communicate radiators, that must release heat, electronics that must keep thinking, and mechanisms that must keep moving? The shield can protect the spacecraft from direct light, but it cannot make every problem disappear. Behind the shield, the machine still has to function, and machines fail long before they turn to ash. The next stage is not a cinematic explosion. It is a quieter and more dangerous narrowing of options. A spacecraft near the sun may survive the heat on its front shield while losing confidence in sensors cooling communication and control. Its weakness may begin not in the wall facing the star, but in the systems trying to live behind that wall. The shield can make a night. Now the spacecraft must keep that night alive. Behind the shield, the spacecraft may still look calm. The cabin, if there is one, remains softly lit. Fans move air through filters. Water circulates through pipes. Screens glow with system status. Outside, the sun pours energy onto the forward shield, but inside the artificial night, nothing needs to feel hot yet. A crew member might hear only the familiar hum of pumps and ventilation. That is what makes this stage so unsettling. Machines can fail quietly. They do not have to melt. They do not have to burst into flame. They do not have to break with a sound anyone can hear. Near the sun, failure often begins as the loss of margin. A component runs warmer than planned. A sensor drifts. A radiator falls slightly behind the heat load. A memory error is corrected, then another. A camera is shut down to preserve it. A communication session is postponed because the antenna geometry is poor. Nothing has ended, but the spacecraft has fewer choices than it had before. The first link in the chain may be a sensor. A temperature sensor on a protected electronics box begins reading a little high. At first, this is not alarming. The value is still inside the allowed range. The cooling system adjusts, moving more heat toward a radiator. Power use changes slightly. Another component warms because the cooling loop has been rebalanced. The software notes the trend. The spacecraft is still healthy, but it is no longer as comfortable. Then the radiator becomes part of the story. Radiators work by releasing heat as infrared radiation into space. They need a view of cold darkness. Near the sun, this becomes difficult because the spacecraft must keep its shield pointed forward, and not every radiator can be placed in the ideal angle at every moment. If a radiator sees too much sunlight, it absorbs energy instead of only rejecting it. So the spacecraft shifts priorities. An instrument is powered down to reduce waste heat. A heater on a colder component is turned off because heat is needed less there. A pump changes speed. The cabin temperature remains stable, but the thermal system is now actively negotiating. The crew may feel nothing, but the ship is spending more attention on remaining ordinary. A small warning appears and clears. Then another warning appears, this time from a different part of the spacecraft. A star tracker used to help the vehicle know its orientation has detected too much glare. It is not blinded completely, but its confidence has dropped. The software compares its reading with gyroscopes and sun sensors. The spacecraft still knows where it is pointing, but now it is relying more heavily on backup information. Nothing is broken, yet the system has become less relaxed. A few minutes later, a cooling pump increases speed. This draws slightly more power. The power system compensates. A non-essential instrument is placed into standby. The change is small, and if this were a normal mission phase, no one would remember it. But near the sun, these small responses begin to form a pattern. The spacecraft is not failing in one place. It is tightening everywhere. Mission control. When it receives the delayed telemetry, may see the story as a sequence of numbers. Temperature trend, pump speed, sensor confidence, instrument status, attitude correction, radiation count, data storage. Each value still belongs inside an acceptable range, but the ranges are no longer comfortable. The spacecraft is behaving like a person walking along a narrowing ledge. Every step is still possible, but fewer movements are safe. If there are humans aboard, the crew may hear a calm notification from the onboard system. Thermal load rising, non-essential operations reduced. Radiation shelter remains available. Communication window delayed. No immediate action required. That last phrase would not be as comforting as it sounds. No immediate action required does not mean no danger. It means the spacecraft is still handling the danger without asking for human intervention. It means the machine is spending its redundancy, using its automatic responses, and trying to preserve the calm interior for as long as possible. The crew remains alive because the spacecraft is absorbing complexity on their behalf. This is how modern spaceflight often hides its drama. The most important events are not always visible. They happen in code, in valves, in sensor fusion, in cooling loops, in the invisible decisions of fault protection systems. A spacecraft can be fighting for its future while appearing almost perfectly still. Near the sun, this hidden fight becomes the main story. The vehicle has to decide what it values most. Science data may be sacrificed to protect attitude control. Communication may be shortened to preserve thermal safety. Power generation may be reduced to avoid overheating. Crew comfort may be narrowed to protect life support. Every decision is a quiet ranking of priorities. And at the top of that ranking is not curiosity. It is continued existence. That is how a cascade can begin. Not all at once. Not dramatically. A spacecraft is a network of dependencies. A cooling decision affects power. A power decision affects communication. A communication decision affects data return. A data decision affects science operations. A thermal warning can lead to an instrument shutdown, which changes the mission plan, which changes the spacecraft's schedule, which changes when it must point an antenna, which may conflict with the shield posture. Near the sun systems do not fail alone. They pull on each other. Electronics are especially vulnerable because they are both essential and physical. A computer may seem abstract from the outside, but it is made of circuits, memory cells, solder joints, processors, boards, and connectors. Heat changes their behavior. Radiation can disturb them. Energetic particles can flip bits in memory or cause temporary faults. Engineers build protection into spacecraft computers, but protection means managing a probability, not removing it from the universe. A single bit flip may be corrected. A cluster of errors may trigger caution. A processor may reset. A redundant computer may take over. A subsystem may enter safe mode. These events are not necessarily disasters. In fact, safe mode exists because spacecraft are expected to protect themselves when uncertain. But safe mode also means the mission narrows. Instruments may shut down. Data collection may pause. The vehicle stops being curious and becomes defensive. A defensive spacecraft is still alive, but it is no longer fully free. The same can happen with sensors. The spacecraft depends on knowing where the sun is, where Earth is, how hot its parts are, what its power state is, what radiation it is experiencing, and whether its attitude is stable. If a sensor stops working completely, the software may recognize the failure. A subtler danger is drift. The sensor still speaks, but its voice becomes less trustworthy. Bad information near the sun is dangerous. If a thermal reading is wrong, the spacecraft may cool the wrong system or fail to cool the right one. If an attitude sensor is confused by glare or radiation, the shield alignment may be threatened. If a particle detector saturates the spacecraft, may not accurately judge the environment. A machine survives by measuring itself and its surroundings. When measurement weakens, control becomes less certain. Communication adds another quiet pressure. The spacecraft may collect valuable data during a close approach, but sending that data home requires power antenna pointing timing and geometry. The sun can interfere with radio signals when the line of sight passes near it. The spacecraft may not be able to rotate freely to aim a high-gain antenna because the shield must remain toward the sun. A low-gain signal may be safer but slower. The best scientific data may have to wait in memory until the spacecraft moves to a better position. This creates a lonely interval. The spacecraft experiences the environment first. Earth understands it later. For robotic missions, that delay is expected. For a crew, it would be psychologically heavier. Imagine knowing that the most dangerous part of the journey is also a time when communication may be limited. The crew watches system displays, listens to the cabin checks, procedures, and trusts onboard autonomy. Earth is still there, but not as an immediate rescuer. The spacecraft must pass through the bright region on its own. Autonomy becomes the machine's survival instinct. It has fault protection routines. It knows which systems are essential. It can shut down non-critical instruments. It can preserve power. It can maintain attitude. It can choose the shield over science, cooling over data safety over curiosity. In a sense, the spacecraft carries a hierarchy of fear, written not as emotion, but as code. Keep attitude. Keep cooling. Keep power. Keep the protected interior alive. These priorities may conflict. A communication antenna wants to move. A radiator wants a better angle. An instrument wants exposure. A solar array wants light, but not too much. A camera wants to see, but glare and heat threaten it. The spacecraft is surrounded by opportunities that are also dangers. Each act of measurement or communication costs something. Near the sun, curiosity has a budget. An instrument aperture opens for a planned observation. For a few moments, a detector sees the environment more directly. It gathers particles, fields, brightness, or plasma data. Its temperature begins to climb. The software watches. The aperture closes. Heat is moved away. The data are stored. Nothing dramatic happened, but the spacecraft has briefly spent part of its safety margin to learn something. This is the moral economy of solar exploration. Knowledge is gathered through controlled exposure. The problem becomes harder if humans are aboard. Human life support is not passive. It produces heat, consumes power, and requires continuous circulation. People release moisture and carbon dioxide. They need exercise equipment, food preparation waste, handling medical monitoring, and psychological space. The more people require, the more systems must function, and the more heat must be removed from the protected interior. The crew cabin is a source of warmth inside a heat problem. That warmth must be managed without exposing radiators to excessive solar energy. If the cooling system falls behind, the cabin may remain livable for a while, then gradually less comfortable, then dangerous. The crew may first notice small changes, warmer air, more frequent system alerts, restrictions on activity instruments, shut down to reduce heat, scheduled sleep disturbed by alarms. The disaster begins as inconvenience. Then the options narrow again. A non-essential experiment is powered off. Exercise is limited to reduce metabolic heat and power draw. A communication session is shortened. The spacecraft rotates a fraction of a degree to improve radiator performance, but only within the shield's safe envelope. The crew moves into a more protected area during a radiation warning. The ship remains functional, but life inside it is now shaped almost entirely by the sun outside it. Radiation can intensify that narrowing. A solar particle event may not be visible through a window. It may arrive as a warning from instruments. Energetic particles rise. The crew is ordered into a storm shelter. Non-essential electronics are powered down or placed in protective modes. Mission control may send advice if communication allows, but onboard systems already know what to do. The spacecraft folds inward, reducing activity, protecting memory, protecting tissue, waiting for the environment to calm. The sun does not need to look different to become more dangerous. A flare or particle event can turn invisible conditions into urgent conditions. This is one reason a crude solar approach would be so difficult. Heat is constant and predictable in some ways. Radiation storms are more variable. The spacecraft must be prepared not only for the steady sun, but for the active sun. That active sun also affects instruments. Detectors can saturate. Cameras can be overwhelmed. Particle sensors can receive more events than expected. Magnetometers may record turbulent changes. Software may have to separate useful data from noise. A scientific instrument near the sun is not simply seeing more of the truth. It is being challenged by the intensity of the truth it came to measure. Too much signal can become a kind of blindness. This is another form of quiet failure. An instrument may be working, but the environment may exceed its useful range. A camera can be flooded with light. A particle detector can reach saturation. A thermal sensor can approach its limit. A communication channel can carry too little data at the required moment. Failure is not always silence. Sometimes it is overload. Material changes at a slower rhythm. A coating that reflects sunlight well at the beginning of the mission may gradually darken or degrade. A surface exposed to radiation may change its properties. Repeated heating and cooling can stress joints. Materials expand at different rates. Adhesives and seals may age. Moving parts may become less reliable. The spacecraft is not just surviving a place. It is surviving exposure over time. A brief pass is different from residence. This is why real close solar missions often move through their harshest environments quickly. Speed becomes part of the survival strategy. A probe can sweep close to the sun, gather data, and move outward again. It does not stay beside the star. It does not make a home there. It crosses the danger zone with a carefully planned trajectory and a limited exposure time. A crewed spacecraft would need the same principle, but with far greater difficulty. It would have more mass, more heat, more complexity, and a larger protected volume. It could not accept the same risks as a robotic probe. It would need more shielding and more redundancy, which would make it heavier and harder to cool. Every extra protection creates another system that must be protected. The machine becomes a web. Pull one strand and another moves. This is why the quiet failure of machines is so important to the journey. It shows that survival near the sun is not determined by a single dramatic limit. The first fatal weakness might be thermal, or electronic, or radiation-related, or communicational, or related to attitude control, or simply the combined pressure of several systems losing margin at once. The spacecraft may never reach a scene of spectacular destruction. It may first become unable to continue the mission safely. A probe might shut down instruments and retreat into safe mode. A crewed ship might abort, turn outward, reduce activity, hide the crew in a protected shelter, and conserve power. The right response to the sun may not be bravery. It may be withdrawal before small failures become irreversible. This gives the journey a quiet realism. The sun does not defeat the spacecraft by anger. It defeats it by making every requirement more expensive, more cooling, more shielding, more pointing precision, more radiation protection, more autonomy, more patience, more energy management, more careful timing, more systems watching other systems. Eventually, even a well-designed machine has to admit the narrowing. Beyond this point, the spacecraft is not merely approaching stronger sunlight. It is approaching the sun's outer atmosphere itself. The environment ahead will not be described well by simple ideas of hot and cold. It will be plasma magnetic fields, charged particles, and solar wind. The sun will stop being only a disk ahead and become something the spacecraft is inside. The machines behind the shield are still working. They have kept the artificial world intact. They have turned sunlight into heat budgets, radiation into warnings, attitude into survival, and communication into carefully timed openings. But the next region will ask a different kind of understanding. It will ask what it means to fly through an atmosphere that is thinner than any air and hotter than imagination. At some point, the journey stops being only a flight toward a bright object. The sun is still ahead, but it is also around the spacecraft in a new way. Its outer atmosphere reaches outward through space, thin beyond ordinary intuition, but physically real. The spacecraft is not approaching a solid boundary. It is entering a region shaped by plasma magnetic fields, charged particles, and solar wind. This region is the corona. From Earth, the corona is usually hidden by the sun's brightness. During a total solar eclipse, when the moon covers the bright disk, the corona appears as a pale, ghostly glow spreading outward. It can look delicate, almost soft, like silver light brushed into the dark sky. That appearance is one of the most beautiful sights in astronomy and also one of the most misleading. For a spacecraft, the corona is not decoration. It is an environment. Entering it is not like entering Earth's atmosphere. There is no thick air pressing against the hull. There are no clouds in the usual sense, no blue sky, no ordinary wind, no breathable gas. The corona is extremely sparse. Its particles are far apart compared with the air around us on Earth. Yet those particles can carry enormous energy, and because many are charged, they respond to magnetic fields that twist and rise from the sun below. This is where the word temperature becomes dangerous if used too simply. The corona can reach temperatures of millions of degrees. That sounds final. It sounds like instant destruction. But temperature in a sparse plasma does not mean the same thing as temperature in dense air or molten material. Temperature tells us about the average energy of particles. Heat transfer depends not only on that energy, but also on how many particles there are and how often they strike a surface. A dense oven at a few hundred degrees can cook food efficiently because countless molecules collide with it again and again. The corona is different. Its particles may be extremely energetic, but there are relatively few of them. They do not transfer heat like dense air. A shielded spacecraft can therefore pass through parts of the corona without being destroyed instantly by contact with a million-degree gas. The main thermal danger remains the intense radiation from the sun and the spacecraft's ability to manage what it absorbs. This distinction does not make the corona safe. It makes it stranger. The spacecraft is flying through a region where everyday intuition fails. Hot does not mean what it means in a kitchen or desert. Atmosphere does not mean something you can breathe. Wind does not mean air moving across your face. Weather does not mean clouds and rain. Every familiar word has to be translated into plasma physics. Plasma is matter in an electrically active state. Electrons are separated from atoms, creating charged particles that respond to magnetic fields. These particles stream, spiral, accelerate, and interact. They do not simply drift neutrally through space. They belong to a moving magnetic environment that begins at the sun and extends far beyond the planets. The sun is not only luminous, it is magnetic. Magnetic fields rise through the visible surface loop into the corona twist over active regions and sometimes reorganize violently. Sunspots mark areas where magnetic activity changes the surface brightness. Prominences arch outward. Flares release bursts of energy. Coronal mass ejections send enormous clouds of magnetized plasma into space. From Earth, these events may be observed as solar activity. Close to the sun, they are the local weather of a star. The spacecraft does not feel this weather as wind on a hull. It measures it. Particle detectors count charged particles. Magnetometers trace the direction and strength of magnetic fields. Plasma instruments sample density, velocity, and temperature. Radiation monitors watch for dangerous events. The spacecraft's body becomes a set of senses designed for a place the human senses cannot enter directly. A crew inside would know the corona through screens. They might see plots changing warnings, updating numbers, rising and falling. They might hear nothing unusual in the cabin. The air might remain cool. The lights might remain steady. Yet the data would show that the spacecraft was moving through the sun's outer atmosphere, through the birthplace of the solar wind, through a region no human body could touch. The sun would be present as measurement. This is perhaps the strangest kind of nearness. A crew member could be closer to the sun than any human has ever been inside the outer atmosphere of a star, and still experience the moment through numbers rather than sensation. The cabin wall would not glow. The air would not suddenly become hot if the spacecraft remained protected. There would be no wind against the skin, no roar, no smell, no color filling the room. The body would be separated from the environment by layers of engineering, but the instruments would be alive with change. A magnetometer might show the field direction shifting. A particle detector might register a faster stream of charged particles. A radiation monitor might climb, then settle, then climb again. Plasma measurements might show the spacecraft crossing from one region into another, not through a visible border, but through a change in density, speed, or magnetic behavior. The sun's atmosphere would announce itself not as a wall, but as variation. This is why the corona is so important to the journey. It teaches that an environment does not need to look full in order to matter. Human senses are poor judges of plasma. To the eye, space may still appear nearly empty. To the instruments, it is structured restless and alive with invisible motion. The spacecraft is flying through a kind of weather that has no clouds. Its weather is made of fields and particles. Its storms may begin in tangled magnetic regions on the sun. Its winds are streams of plasma expanding outward until they fill the spaces between planets. Its pressure is not felt on the face, but measured in instruments. Its danger is not always seen, but calculated in dose, flux, temperature, and charge. For a listener on Earth, this may be difficult to picture, because Earth teaches weather through the body. We feel humidity, cold, heat, rain, pressure, gusts of wind. Near the sun, the body has been removed from direct contact. The spacecraft must become the nervous system. It senses what the body cannot, then turns that invisible world into warnings, plots, and stored data. The closer we come to the sun, the more seeing becomes translation. And the more translation we need, the clearer it becomes that human beings are visitors only through their machines. That may sound less dramatic than direct experience, but near a star, it is the only safe way to perceive. Eyes cannot look directly. Skin cannot touch. Lungs cannot breathe. ears cannot hear sound through vacuum. The spacecraft becomes the body that senses filters and translates. In this region, the solar wind becomes more than a phrase. Far from the sun, the solar wind is the stream of charged particles flowing outward through the solar system. It shapes planetary magnetospheres, helps form comet tails, drives space weather, and defines the sun's extended influence. Inside the corona, the spacecraft approaches the place where that wind is being formed and accelerated. It is no longer only observing the result, it is entering the source region. This gives the journey a wider scale. Earth is not orbiting an empty space with sunlight passing through it like a distant beam. Earth orbits inside the sun's extended domain. The space between planets is crossed by particles, radiation magnetic fields, and flows. The sun is the center, not only gravitationally, but environmentally. It fills the solar system with more than light. Inside the corona, that truth becomes physical. The spacecraft is still far from the visible layer, but it has crossed into a region that belongs to the sun. This is why phrases like touching the sun can have a scientific meaning when applied to missions that enter the solar atmosphere. A probe can pass inside a boundary where solar material remains connected to the star before streaming outward. It can sample particles and fields in the sun's own outer atmosphere. But this kind of touching is not contact with a surface. It is entry into a gradient. That difference matters. With a planet atmosphere and surface are easier to imagine. The air thickens, the ground arrives, the lander touches down. With the sun, layers do not become a floor. They become different conditions of plasma, opacity, temperature, density, and radiation. The corona is a layer, but not a room. The photosphere is visible, but not ground. The corona itself contains one of solar science's great puzzles. The visible surface of the sun is thousands of degrees, but the corona above it reaches millions. This seems backward. We expect things to cool as we move away from the source of heat. The sun's outer atmosphere refuses that simple expectation. Scientists study waves, magnetic reconnection turbulence, and other processes to understand how energy moves upward and heats the corona. For the journey, this mystery is useful because it deepens the sun's strangeness. The sun is not a simple hot ball fading outward. It is layered, dynamic, and magnetically complex. Energy does not move through it in one obvious way. What we see from Earth as a smooth disk is only the visible face of a much more restless system. A spacecraft passing through the corona may encounter changing magnetic structures. It may move through streams of faster and slower solar wind. It may detect bursts of energetic particles. It may record turbulence waves and sudden shifts in field direction. The environment is thin, but it is not empty. It is sparse matter organized by powerful forces. This gives the section a different kind of tension. The spacecraft is not being crushed by atmosphere. It is not flying through dense flame. It is moving through something ghostly and active, a place where physical danger is measured in radiation particles, fields, and heat balance rather than in the familiar resistance of air. The danger is less visible, but not less real. For instruments, the corona is both treasure and threat. This is where data are most valuable. Measurements here can help explain how the solar wind accelerates, how energetic particles move, how magnetic fields shape the outer atmosphere, and why the corona behaves as it does. But every observation requires exposure. An instrument that opens to the environment must survive the particles' radiation and heat associated with that opening. Again, knowledge has a cost. A detector samples. A camera peers through a protected path. A magnetometer records. A plasma instrument counts. The spacecraft gathers a small fraction of the sun's behavior and stores it for transmission to Earth. Then it protects itself again. Near the sun science is not an open window. It is a controlled exchange. The crew, if imagined aboard, might feel the paradox deeply. They would be inside the sun's atmosphere and yet physically separated from it by every layer of the spacecraft. They could not open a hatch, could not look directly, could not feel the plasma, could not hear the solar wind. Their experience would be intellectual, procedural, and emotional. They would know where they were because the spacecraft told them. A display might show the heat shield temperature. Another might show radiation levels. Another might show magnetic field direction. Another might show the status of cooling loops, antennas, instruments, and attitude control. The cabin would remain human only because the machine kept translating the star into manageable numbers. Outside, the corona would continue moving according to physics, indifferent to human presence. Inside, the crew would watch the data and understand that their senses had been replaced by instruments. This is one reason the sun becomes less like an object as the journey continues. Objects can be viewed from outside. Environments surround and condition you. Inside the corona, the spacecraft has crossed into the sun's environment. The bright disk still lies ahead and below, but the surrounding space is no longer merely space between the ship and the sun. It is part of the sun's extended atmosphere. Still, the corona is not the final impossibility. Its thinness, strange as it is, allows a shielded spacecraft to pass through parts of it. The more severe problem lies closer to the visible sun, where the photosphere emits the light that fills the solar system. The corona teaches that temperature and heat transfer are not the same. The photosphere will teach that radiation intensity can become overwhelming even without any solid surface at all. As the spacecraft moves inward, the sun fills more of its sky. The shield remains forward. The protected systems remain behind it. The artificial night still exists, but the geometry becomes more severe. The light comes from a larger, apparent disk. The environment becomes more dominated by the star's visible layer. The question of where heat can go becomes harder. The spacecraft begins to lose the clean separation between one dangerous direction and all other safe directions. The corona has broken the ordinary idea of heat. It has shown that a 1,000,000-degree atmosphere can be too thin to behave like a furnace, while still remaining a dangerous plasma environment. It has shown that the sun's weather is magnetic, invisible, and energetic. It has shown that touching the sun means entering layers, not reaching land. Ahead waits the visible surface, which is not a surface in the human sense, and as the spacecraft approaches it, the problem will no longer be the ghostly heat of sparse plasma. It will be the unsoftened light of a star arriving from a glowing layer that no human machine could treat as a destination. The corona was strange because it forced temperature and heat apart. It could be millions of degrees, yet thin enough that a shielded spacecraft could pass through parts of it for a limited time. That did not make it safe. It made it unfamiliar. The danger lived in radiation particles, magnetic fields, and heat balance more than in the simple image of a dense furnace. Closer to the visible sun, the lesson changes. Now, the main problem is not the thinness of the outer atmosphere. It is the overwhelming power of the layer we see from Earth as the sun's surface. This layer is the photosphere. It is the bright face of the sun, the region from which most visible sunlight escapes into space. Every ordinary day on Earth begins with energy that last emerged from this layer. From far away, the photosphere looks sharp. The eye sees a bright round disk with an edge. That is how vision turns light into shape. The deeper layers of the sun are opaque to visible light, so the photosphere becomes the apparent boundary. It gives the sun a face. It lets the mind say there is the surface. But the mind is borrowing language from planets. The photosphere is not ground. It is not a crust. It is not a floor. It is a glowing layer of plasma, a region where the sun becomes visible to us, not a place where a spacecraft could rest. Approaching it is not like approaching a landing zone. It is like moving closer to the source of daylight itself. This is where the physical impossibility becomes more direct. Near Earth, sunlight has spread across a vast distance. At Mercury-like distances, it has multiplied. At Parker-like distances, it becomes hundreds of times stronger than at Earth. Near the photosphere, the spacecraft approaches a region where the sun fills far more of the surrounding sky, and where radiation is no longer simply a strong beam from a distant disk. It becomes the dominant condition around the vehicle. The shield still faces the sun, but its task becomes increasingly impossible. At earlier stages, the shield could create a protected shadow. One side of the spacecraft endured direct sunlight. The other side remained in artificial night. Radiators could reject heat into dark space. Instruments could hide and look through protected paths. The spacecraft's life depended on keeping a clear division between exposed and protected. Near the visible layer, that division begins to weaken. The sun occupies more of the view. The radiation field becomes more intense. The shield receives an enormous heat load. Any exposed edge, seam, aperture support, or protruding component becomes a potential failure point. The protected shadow still exists in principle, but the spacecraft must work harder to keep it meaningful. Heat also has fewer places to go. This may be the hardest engineering problem to feel intuitively. A spacecraft must reject its internal heat. Computers, pumps, batteries, life support, motors, instruments, and people all produce heat. That heat has to be carried to radiators and released into space. Radiators need a cold view. They need darkness. They need to avoid absorbing more energy than they emit. Near the photosphere, the sun begins to steal the sky. A radiator cannot simply point anywhere and cool itself. If it sees too much of the sun, it absorbs radiation. If it is hidden too deeply, it may not have enough view to reject heat. If it is angled poorly, it loses efficiency. The spacecraft becomes trapped between two needs: hide from the sun and radiate heat away. Closer in satisfying both becomes increasingly difficult. A crude vehicle would make this problem far worse. A robotic probe can be compact. It can place delicate systems behind a shield and accept limited operation during brief, close approaches. It does not need a comfortable cabin, breathable air water, recycling exercise, space, psychological space, medical support, food storage, or emergency shelter for living bodies. A crewed spacecraft must be a world, not just an instrument. Worlds produce heat. The people inside produce heat. Their life support systems produce heat. Their computers, pumps, lights, carbon dioxide, scrubbers, water processors, and control systems produce heat. All of that must be moved and rejected while the ship is near the most powerful source of heat in the solar system. The crew is protected only if the machine can maintain a narrow internal condition against an increasingly impossible exterior. The first failure might not be the shield burning through. It might be the cooling system losing the race. Internal temperatures rise. Non-essential systems shut down. Crew activity is reduced. Instruments are powered off. The cabin remains safe for a while, but every action is governed by thermal budget. The spacecraft becomes less like an exploring vessel and more like a shelter trying to conserve its own order. Electronics would also enter dangerous territory. They do not need to melt to fail. They need only exceed their safe operating range, accumulate radiation damage, or experience too many errors. A processor reset near Earth may be manageable. A processor reset near the visible sun, when attitude control and thermal protection depend on rapid response, is more serious. Every computer is now part of the shield because without control, protection loses shape. Optics become vulnerable as well. Cameras may be blinded by brightness. Detectors may saturate, filters may heat, apertures may be opened only briefly, if at all. The spacecraft came to approach the sun, but the closer it gets, the less it can allow the sun into its instruments. Observation narrows to carefully filtered fragments. Direct seeing becomes impossible. Human seeing would be even more limited. The crew could not simply look out. A window facing the sun would be a dangerous weakness unless deeply shielded and filtered. The star would be known through images processed by instruments, through graphs, through warnings, through telemetry. The closer the humans came to the source of light, the less light they could safely receive. There is something quietly powerful in that reversal. The sun becomes too visible to see. At this stage, even the idea of a window becomes almost symbolic. On Earth, a window is an opening to the world. In a spacecraft near the visible sun, it would be a carefully controlled vulnerability. Any transparent material must survive radiation, thermal stress pressure difference, and the intense brightness outside. It would need filters, shutters, coatings, and strict rules. The crew might be closer to the sun than any human in history, and yet be forbidden from looking at it in any ordinary way. That prohibition is not only about eyesight, it is about admitting that direct experience has reached its limit. The sun is now too intense to be treated as scenery. It cannot be framed safely like a planet through glass. It cannot be watched casually as a glowing horizon. It must be reduced, filtered, dimmed, translated, and broken into data before it can enter the human world. This is where the spacecraft's interior begins to feel almost paradoxical. The closer it comes to the source of all daylight, the more its inner world must become dark, controlled, and indirect. Screens replace windows. Filters replace sight. Telemetry replaces sensation. The crew does not approach the sun by opening themselves to it. They approach by being more completely sealed away. The same paradox appears in cooling. A machine that is too cold can be warmed. A machine that is too hot must find somewhere to send its heat. Near Earth, dark space offers that escape. Near the visible sun, cold space is harder to use because the sun occupies more of the thermal geometry. The spacecraft cannot simply radiate in all directions with equal freedom. It must choose where heat can leave without inviting more heat in. A radiator looking too close to the sun becomes less useful. A radiator hidden too well may not see enough cold space. A radiator placed poorly may create thermal stress somewhere else. The spacecraft is not only trying to survive the heat outside, it is trying to dispose of the heat inside without exposing itself to more of the thing it is escaping. This is the trap of the visible sun. The spacecraft needs darkness, but the sun is taking over the sky. It needs to reject heat, but the environment is flooded with radiation. It needs to see, but the light is too powerful. It needs to remain a separate interior, but the exterior is becoming too dominant. At some distance, these contradictions stop being design challenges and become physical limits. The photosphere itself is roughly thousands of degrees Celsius. Its temperature is beyond ordinary materials, beyond lava, beyond the conditions a human habitat could treat as an external environment. But temperature, again, is only part of the story. The real problem for a spacecraft is radiative power. How much energy arrives? How much is absorbed? How much can be reflected? How much conducts inward? And how much can be rejected? Near the photosphere, that balance fails for any realistic human system. The heat shield might hold for a short time under some extreme condition, but the spacecraft is more than a shield. It is structure wiring tanks, electronics, seals, insulation instruments, radiators, and perhaps a living interior. A spacecraft is a maintained set of differences. Hot outside, cooler inside. Vacuum outside, pressure inside. Radiation outside, shielded tissue inside. Chaos outside, ordered system inside. Near the visible sun, those differences collapse. The exterior becomes too dominant. The shield receives too much energy. The radiators lose their cooling advantage. The internal systems generate heat that cannot be removed. The margin for attitude error vanishes. Materials deform, coatings degrade, sensors saturate, and the spacecraft's ability to remain organized begins to fail. There is no need for a dramatic impact. There is no ground to hit. If the spacecraft continued downward, it would enter denser solar material. The plasma would not become a surface. It would become a deeper environment. Density would rise. Pressure would rise. Energy transport would change. The spacecraft would not touch down. It would be engulfed by the conditions of a star until its structure and systems no longer existed as a spacecraft. This is where the word surface becomes a trap. The photosphere is visible because light escapes from it. It is not solid because we can see its outline. The sun's edge is an optical boundary, not a platform. It is the place where the star becomes transparent enough for photons to leave and travel across the solar system. From Earth, that looks like a surface. Up close, it is a region. A region cannot hold landing legs. It cannot support a wheel. It cannot receive a footprint. It cannot be crossed into and then stood upon. The surface idea is powerful because human life is built around surfaces. We stand on ground, sit on chairs, cross floors, walk through doors, sail over water, and look toward horizons. Our language carries solid world assumptions everywhere. To say approach the sun almost automatically suggests that there is something to approach in the way a cliff island or planet can be approached. The sun teaches another kind of reality. It is layered without being land. It is structured without being solid. It has a visible face without having a floor. Its plasma moves, convects, radiates, and responds to magnetic fields. Granules rise and fall across the photosphere like enormous cells of hot material. Sunspots mark magnetic regions, cooler than their surroundings, but still unimaginably hot in human terms. Flares and eruptions can grow from magnetic stress. This is not a calm, glowing shell. It is a restless, luminous boundary inside a star. A spacecraft nearing it would not find the final stage of a descent. It would find the end of survivable definitions. Shield, radiator, cabin, antenna, camera, sensor, computer, life support system. All of these words assume that the machine can keep inside and outside separate. The visible sun is the region where that separation becomes physically unsustainable. For a realistic crewed journey, the mission must end far above this. It must turn back or pass no closer than its shield cooling radiation protection and control systems can tolerate. It cannot continue toward the photosphere in any meaningful human way. The closer it goes, the less the question is, how would the crew experience it? And the more it becomes, which system fails first? And how fast does the failure cascade? The answer depends on design, solar activity, distance, and time. The conclusion does not. No human spacecraft could operate near the visible surface as a destination. It could not hover there as if above a planet. It could not land. It could not remain. It could only lose the balance that allowed it to be a spacecraft. That realization gives the sun a strange intimacy. Every day, light from this layer arrives on Earth as something gentle enough to live by. It warms rooms, feeds leaves, turns water to vapor, moves climate, marks time, and makes vision possible. Yet close to its source, the same light would overwhelm the machines built to approach it. The distance between life and destruction is not moral. It is orbital. The sun is life-giving because Earth is far enough away. The spacecraft has shown this step by step. The sunlight that felt ordinary became raw energy. The loss of Earth's protection revealed our dependence. The inverse square law turned distance into danger. The shield created a narrow artificial night. Machines began to fail in margins. The corona broke simple ideas of heat. Now the photosphere breaks the idea of a reachable surface. The final threshold is almost here. Ahead, there is no world waiting. No ground, no shore, no landing zone. Only deeper layers of a star, each less compatible with the boundaries a spacecraft needs to survive. The journey has approached the visible sun and found that visibility is not arrival. The next realization is the simplest and the most difficult. There is no place to land. The final answer is not a scene of arrival. It is the disappearance of arrival itself. A spacecraft can approach Earth and enter atmosphere. It can approach the moon and descend toward dust. It can approach Mars and measure altitude above ground. It can approach an asteroid and match its slow rotation. Even gas giants, though they have no solid surface in the simple sense, still invite the imagination to descend through clouds and pressure layers. The word approach feels meaningful because the mind expects some boundary, some change, some place where the journey becomes contact. The sun refuses that expectation. It has layers, but not floors. It has a visible face, but not land. It has an atmosphere, but not air. It has motion, but not weather in the earthly sense. It has edges in images, but not edges a spacecraft can touch. Every word brought from planetary travel begins to lose precision. The spacecraft does not arrive at the sun. It enters conditions. That difference is the final conceptual turn of the journey. Arrival suggests a stable relationship between traveler and destination. A lander arrives when the ground supports it. A ship arrives when water holds it. A station receives a docking spacecraft because structures meet structures. The sun offers no such support. It is plasma held by gravity, pressure, radiation, and magnetic fields. It is process, not platform. If a spacecraft tried to continue downward beyond the visible layers, it would not find a hidden crust beneath the light. It would move into denser and hotter solar material. The outside would become less like space and more like the interior environment of a star. Pressures would rise. Energy transfer would intensify. The spacecraft's materials would lose their meaning as engineered boundaries. Its shield, once the front of a protected night, would become only matter inside a larger plasma system. The machine would lose separateness. That may be the most accurate way to imagine the end. A spacecraft is an organized separation from its environment. Inside is pressure, temperature control, electricity information, oxygen, and structure. Outside is vacuum radiation, plasma, and darkness. The spacecraft survives by keeping those categories apart. Near and inside the sun, the categories fail. The shield can no longer keep enough energy out. The radiators can no longer release enough heat. The computers can no longer remain cool and reliable. The sensors can no longer interpret the environment within useful limits. The structure can no longer preserve its shape. The cabin, if one existed, can no longer remain a small Earth. The outside overwhelms every boundary that made an inside possible. This is not landing, it is unmaking. The sun does not need to strike like a weapon. It does not need a surface impact or a violent collision. The spacecraft ends because the conditions required for spacecraft existence vanish. Temperature, radiation pressure, heat flow, and plasma environment move beyond the range where human engineering can maintain order. This is why touching the sun has to be understood carefully. A probe can enter the sun's outer atmosphere. It can cross into regions that are physically part of the sun's extended environment. It can sample particles and magnetic fields. It can measure the solar wind near its source. In that scientific sense, humanity can touch the sun's atmosphere through machines. But touching an atmosphere is not landing on a surface. It is more like entering the outer reach of something too large and too fluid to meet in the ordinary way. Even that comparison is limited. The sun's atmosphere is plasma, not breathable air. Its wind is charged particles, not moving gas against skin. Its storms are magnetic and radiative, not rain and thunder. The closer the journey goes, the more every metaphor has to be corrected. The sun keeps asking language to become more careful. There is no wall. There are gradients, density changes, temperature changes, opacity changes, magnetic behavior changes, radiation changes. The names of the layers help scientists describe these changes, but the names do not turn the sun into a building. Corona, chromosphere, photosphere, convection zone, radiative zone, core. These are not rooms stacked neatly downward. They are regions of physics within a star. A spacecraft cannot choose one as a landing site. It can only survive some outer regions for limited times, under strict protection, then fail as the conditions deepen. This is the answer that makes the whole step-by-step journey quieter than a disaster story. The sun is not a trap with a final dramatic door. It is a star. The closer you go, the more it strips away the assumptions that made the journey seem imaginable. First, the assumption that sunlight is gentle. Then the assumption that space is simply cold. Then the assumption that more sunlight is just more brightness. Then the assumption that strong materials are enough. Then the assumption that machines fail only when they visibly break. Then the assumption that temperature always means what it means on Earth. Then the assumption that a visible surface is a place. At the end, even the phrase getting close has changed. Close to what? Close to the photosphere, which is visible but not solid. Close to the corona, which is atmosphere but not air. Close to the sun, which is a body but not a world. The spacecraft has moved toward the star, but the star has not become a destination. It has become more completely itself. That is the final lesson. The sun is not scaled to human arrival. It is scaled to gravity, fusion, mass, radiation, and time. Deep inside nuclear fusion releases energy under conditions far beyond anything human life could endure. That energy moves outward through layers of the star, changing form and direction countless times before emerging as light. By the time it reaches Earth, it has become the daylight that seems so familiar. But near its source, it belongs to a physical regime in which human presence is temporary at best and impossible beyond a limit. The crude version of the journey would end long before the final layers. A realistic mission would have to turn away while the spacecraft still had margin. It would not wait for the first fatal cascade. It would not descend until shield failure became inevitable. Survival would mean respecting the boundary before the boundary looked final. Engineers would plan the closest approach not around bravery, but around heat, load radiation, dose, cooling capacity, autonomy, and retreat. Turning back would not be failure. It would be the only form of success. This is what real solar exploration already teaches. Our closest probes do not conquer the sun. They pass near it in carefully planned arcs. They hide behind shields. They operate autonomously. They collect measurements during limited windows. They return data when geometry allows. They survive by accepting that the sun can be studied only through respect for the conditions it imposes. A probe may come closer than any machine before it. Then it moves outward again. That outward movement matters. It shows that the sun allows encounters, not residence. A spacecraft can cross the edge of the solar atmosphere, listen, measure, endure, and leave. It cannot settle there. It cannot build a stable human presence near the visible layers. The sun is not a destination waiting for infrastructure. It is the source environment of the solar system. The phrase sounds almost peaceful when stated plainly. The sun allows encounters. It does not allow arrival. This also changes the way Earth feels at the end of the journey. Earth is not merely the starting point. It is the place where the sun becomes survivable. It is the system that turns stellar radiation into climate-color food and time. Its distance is not emptiness. Its atmosphere is not decoration. Its magnetic field is not an abstract diagram. Its nights, clouds, oceans, and winds are all part of the reason daylight can be gentle. We do not live under the sun in its raw form. We live under Earth's translation of the sun. That translation is everywhere. It is the blue sky that hides the blackness of space during the day. It is shade that still contains breathable air. It is sunset that gives the land time to cool. It is the ozone layer that reduces dangerous ultraviolet light. It is the ocean storing heat from one season into another. It is the plant leaf turning photons into sugar. It is the human eye adapted to a brightness filtered by atmosphere and distance. A spacecraft moving inward leaves that translation behind. Step by step, it hears the original language more directly. That language is not cruel. The sun is not an enemy. It does not notice the spacecraft. It does not choose to destroy. It shines because it is a star. It releases energy because gravity and fusion sustain its structure. It emits particles because its plasma atmosphere flows outward. It shapes the solar system because its mass and energy are enormous. The danger comes from mismatch. Human life is narrow. It needs particular temperatures, pressures, chemistries, and radiation levels. Machines are broader, but still limited. They need materials that hold shape electronics, that remain reliable radiators, that can dump heat sensors, that can measure, and software that can act. The sun exists outside those comfortable ranges, except at great distance. Distance is part of habitability. That may be the most important quiet conclusion. The space between Earth and the sun is not simply a gap to be crossed. It is part of what makes life possible. Too far, and sunlight fades. Too near, and energy overwhelms. At the right distance, with the right planet, the sun becomes a source of life rather than a force that erases boundaries. The journey toward the sun therefore gives back a different kind of wonder. It does not end with a flag or a footprint. It ends with the understanding that no footprint belongs there. It does not end with a spacecraft resting on a glowing plane. It ends with the recognition that the plane never existed. The visible surface was always a threshold of light, not land. There is also a deeper reason the sun cannot be treated as a destination. A destination is something that remains itself while you arrive. A mountain does not stop being a mountain when you climb it. A shoreline does not stop being a shoreline when a boat reaches it. The moon remains the moon beneath a lander's feet, but the sun changes the meaning of arrival because the traveler cannot remain itself. A spacecraft approaching too deeply into the sun does not arrive as a spacecraft. Its systems lose the conditions that made them systems. Its materials lose the conditions that made them useful materials. Its sensors lose the ranges in which they can sense. Its computers lose the temperature and radiation environment in which they can compute. The vehicle's identity depends on boundaries, and those boundaries are exactly what the sun removes. So the final limit is not merely distance. It is identity. How close can a spacecraft get before it stops being the kind of thing that can continue the journey? How close can a human-made system approach before the environment no longer permits pressure, cooling communication structure, and control to remain separate from the star around it? The answer is not marked by a sign in space. It is marked by the failure of maintained order. This is why a realistic solar journey would never aim for contact in the old sense. It would aim for a closest approach. That phrase is more honest. It admits that the spacecraft is not arriving. It is passing near surviving briefly, measuring what it can, and leaving before the conditions become too severe. The mission's success is not touching the sun, but returning from the edge with knowledge. That makes the achievement quieter but also more profound. Human exploration is often imagined as reaching places, planting flags, standing on surfaces, taking steps. But some places in the universe are not places for standing. They are places for instruments, for mathematics, for careful passes through hostile regions, for humility before conditions that cannot be made human. The sun is one of those places. We can know it but not inhabit it. We can approach its atmosphere but not rest upon it. We can receive its light every day but never stand where that light begins. The final image is not a landing site. It is a spacecraft turning away while it still can. Behind it, the sun continues to radiate immense and indifferent. Ahead, as it moves outward, the light gradually thins. The shield remains forward until the danger eases. Radiators find easier darkness. Instruments cool. Communication improves. The artificial night is still carried for a while, then becomes less urgent. Earth distant and blue becomes imaginable again, not only as home, but as protection. The crew, if they existed, would return with no sample of the surface. There was no surface to sample. They would return instead with knowledge that a star is not a world, that light is physical, that survival depends on distance, and that the sun we love from Earth is possible only because Earth stands far enough away to soften it. That understanding is quieter than fantasy, but deeper. A human cannot land on the sun. A human can understand why. And perhaps that is the more beautiful achievement. To know the limit clearly. To send instruments where bodies cannot go. To measure plasma radiation and magnetic fields. To learn from the outer atmosphere of a star while accepting that no traveler will step onto it. To look again at ordinary daylight and recognize the immense journey it has already made. At the end of the descent, the spacecraft does not touch down. It carries back a different answer. Not the triumph of arrival, not the image of a surface, only the knowledge that the light we live by comes from a place where no one can stand. By the end of this journey, the sun may feel less familiar than it did at the beginning. It is still the same star that rises each morning and fills the day with light. But that light now carries another meaning. From Earth, it reaches us softened by distance, atmosphere, clouds, water, and the slow turning of the planet. Closer in the same light becomes an environment no human system can endure for long. The real answer was never simply that you would burn. The truth is more gradual and more revealing. Earth's protection would fall away. Sunlight would multiply. The spacecraft would have to hide behind a shield, manage heat, survive radiation, preserve communication, and keep its machines working while every margin narrowed. Nearer still, the corona would break ordinary ideas of heat, and the photosphere would break the idea of a reachable surface. And that makes the sun feel more mysterious, not less. The science does not remove the wonder. It makes the wonder more precise. The familiar disk in the sky becomes a layered plasma star. The warmth on your skin becomes energy that crossed space after leaving a surface no body could approach. The safety of daylight becomes evidence of a planet doing countless quiet things correctly. The journey toward the sun ends by returning our attention to Earth. Not because Earth is less interesting, but because Earth is the reason the sun can be experienced as beauty rather than danger. A blue sky, a cloud, a shadow, an evening breeze, each one is part of the long protection standing between life and raw starlight. And finally, arrival itself would disappear. There would be no ground, no shore, no landing zone, no final place where the journey could end like a journey to a planet. The sun is a star, a layered body of plasma and magnetic fields, giving life from afar while remaining impossible up close. Perhaps that is the quiet wonder of it. Every day we live by energy from a place we could never visit. We turn our faces toward its warmth, measure our seasons by its path, grow food from its light, and sleep beneath skies shaped by its gravity. Yet if we tried to come too close, the very thing that sustains us from a distance would calmly undo the systems keeping us alive. The sun does not need to be reached to be understood. It only needs to be seen more honestly, not as a simple bright disk in the sky, but as the star whose light becomes gentle only because Earth is far enough away to make it so.